Good morning. Our senior design project is ALBA, an autonomous load-bearing assistant robot. My name is Dshante Smith.
My name is Luciano Boniche.
And I'm Hernandez.
Here is the presentation outline in which we will follow. We will start with the problem statement, a little background information on robots, our prototype design and the construction process, how we integrated global learning, and the Gantt chart and the division of responsibilities. The problem statement. We find that loads are heavy for your average employer. Also, a lot of time and energy is wasted trying to carry these heavy objects. And the robots that exist today are very expensive. Literature survey. Autonomous robot. Autonomous robot can be defined as a device that has the responsibility of performing tasks for its users. And when we say automatic, it is programmed exactly the way it will perform. An autonomous robot is considered to be a closed loop, which means that it is dependent on the sensor. In our case, the sensor is the Pixie camera. And it uses this sensor to give a response. When designing a robot, it is imperative to select a drivetrain. A drivetrain is similar to a powertrain inside your vehicle. There are 5 different types of drivetrain. You have tank drive, spur drive, slide drive, holonomic, and mechanism. Then you have wheels, as this is responsible for the movement of the robot. There are 3 different types of wheels. You have traction, which is commonly used, mechanism, and omni. Here's the related standards. These are the ISO, the International Organization Standardization of Standards. Then we have the ASI and the ASTM.
These are the alternate designs which we considered. The first one to your left is the initial design, which we considered before even thinking of what load we're going to use or what sensors we're going to use. This one wasn't as ideal as we expected because of the load distribution and the space for the load, which wouldn't be enough since we had to narrow it down from the front. So we decided to go with the tank drive, which was looking really good. It could carry loads, high torques, drive on any terrains, but then we went into the tank drive itself, and it was very expensive, even for a scaled version of like 1/16. It was well over $1,000 for the drivetrain alone. So we did some improvements, and instead of 200 pounds, which we previously were thinking of, we went for 400. We replaced the tracks with wheels. We exchanged the transmitter and receiver with a tracking camera sensor. And the reason were to reduce the final product, improve efficiency, decrease the cost, and make it less complex. This was our final conceptual design. We constructed it made with 2 Merit MP3 motors, Arduino microcontroller, our saber-tooth driver, and 2 12-volt batteries. Our structure design was made with the ASTM 836 steel, which was 25-inch by 22-inch with a cross-section of 1 inch square with a thickness of 1/16 inch. We applied the load of 400 pounds evenly on the top of the structure with the fixtures at the mounting plates, which were fixed at the Z direction only. We did a welding analysis, and it gave us a recommended weld sizing of 0.038 inches, but we went with a 0.1 inch to make it safe. Simulation plan, as we said before, we used a 400-pound load with the 836 steel, which had a yield strength of a little over 36,000 psi. With the stress analysis, we found a maximum stress of a little over 21,000 psi, which gave us a 1.7 factor of safety. And with the displacement analysis, we found a very small displacement of 53 thousandths of an inch. This is our prototype design. It's an open source to enable users to adapt to ALBA. You can customize the programming very easily to change the distance where that's going to stay or keep away from you, as well as the speed for the motors as you're liking. It's scaled to carry 400 pounds and contains a camera sensor that follows you with colors.
For the construction here, we started in two parts. We did kind of the chassis before, and then we did the electronics. So we started here with welding a frame together. We attached the motors here. Here we see the motor with the wheels, and here we see the front wheels mounted right here in the front, and then the brackets for the batteries on the bottom, and lastly the batteries themselves. For the electronics, we had to kind of design it beforehand before we started buying everything. We showed, right here we're showing how the Arduino connection would connect to the saber tooth, the motor driver, and how it's all going to kind of look on the robot itself. Here this is a camera sensor, and here's kind of the last picture. For the electronics design, this is the overall design. We have two 12-volt batteries in series to make 24-volt power source. We have 100 amp in between the switch and the saber tooth driver, which powers the two motors separately with 60 amp fuses in between. From there we have two channels going from the saber tooth to the Arduino with a ground, which sends the signals. It takes in the information from the Pixie camera, the sensor, sends the information to the saber tooth, and it can drive and actuate the motors. And the Arduino and camera are powered by a separate 9-volt battery source. Here's kind of the data flow of how it works. Basically, the camera itself takes in 4 values, takes in X and Y location of the object that it's tracking, and it also takes in the width and height of the actual object itself, so it can tell the area of it. Basically, you can calculate that. It has a feedback control loop using there's pan and tilt servos right here to actually actuate the camera to track and follow the target. With that information, we can send signals to the saber tooth, which are 1,000, 2,000 microsecond pulses, which convert into an analog voltage to the DC motors. We did 3 experiments to test the effectiveness of the robot. The load and velocity test here, you can see there's a tape set up that's 10 feet, and we set the target, which is a red shirt, 13 feet in front of the robot itself. Here we did 3 tests for the load and speed test, which was no load, 200-pound load, and 400-pound load. And so basically we would turn it on, and it would just run forward, and we'd measure the time it took to traverse the 10 feet, and we got average velocity and average acceleration over time. The acceleration, we used a more high-tech version of trying to get the acceleration data. So we used an accelerometer on a smartphone, and we actually measured the acceleration throughout its entire course. We also did a vibration study to check the vibrations on the motor when it's moving at its slowest speed versus its highest speed. So these are the results for the load and speed test. Up here we have, like I said, the no load 200-pound load, 400-pound load. We got an average of 4.02 seconds, 3.73 seconds, 3.48 seconds. So it's very slightly between the no load and the 400-pound. And then we had, over those 3 tests, we checked the average acceleration over those, took the time, divided by the time, and found we have 1.62, 1.39, 1.21 average acceleration. This is the accelerometer data that we received. We didn't realize it was going to be so sensitive when we put it on, and we have a lot of noise going on. But we figured that when we looked at the time that we actually tested this, we found that these spikes were more of just noise coming from hitting or driving on the actual floor itself, being rough surface and being on tile, and you bounce and hit certain points. So we saw that the max peak of the acceleration was actually right before this big drop here, and it was close to about 2 meters per second squared. This is a vibration response of the system that we measured with a Polytech vibrometer. We saw that at 140,000 hertz and 115 hertz, we had 2 peak spikes that we were looking into, and we didn't have any really high rotation speed, so we weren't worried about any excessive vibrations. This is just a quick example of how it operates. That's kind of how we did the load and speed test. You can see it stops a certain distance from the person. I weigh about 190 pounds, so this is taking me without a problem. And this shows how it follows the person. She got scared and started running away. But That is essentially how the entire thing would operate. You can put loads on and take them off.
Sure.
Here's the cost analysis. As you can see, our two most expensive parts was the motor driver, which was a saber tooth, and the motors, which was from a wheelchair. The wheelchair motor was $155 and the saber tooth was $189. We came to a total of $801.54, in which our budget was $800. So we went over by $1.54.
Wow. I think that's what
The
that
standards
means.
used, we use the ISO 7000, recycling and disposal of batteries. This will assist with pollution. So we would recommend our users to carry the battery to its local recycling plant. Global learning. ALBA can be used through a wide range of users, from elderly to children. Elderly, it will assist with their independency, and it will eventually give employment opportunities. Children can also use ALBA as engineering-related projects in school. ALBA would also contribute to reducing injuries. A lot of back injury occur in the workplace, especially those who are mail carriers, warehouse workers, and even children and students who have to carry these heavy backpacks every day. It's also environmentally friendly, as no emissions is released into the air, and multinational product, as we have a manual in 3 different languages. Lifelong learning. We were able to build skills on team, working as a team, problem solving, coming up with solutions, managing our time, real life testing, working on hands-on experience, interpreting test results, and getting a better concept design. Here's the Gantt chart. Although everything didn't go as planned sometimes, we were able to successfully produce ALBA, as you can see. The division of responsibility. Luciano was responsible for the simulations and the structural plan. Joseph was responsible for the construction and the testing, and I was responsible for the financials and experimental plan and organization. In conclusion, ALBA provides an alternate way of transporting your heavy loads, and at the same time, it's more efficient. It is designed to be multi-purpose. It provides diversity among its users, and it's very inexpensive compared to what's on the market today. In the future, we hope to have ALBA fully automated, obstacle avoidance, and to add advanced techniques such as control features and make it more scalable. That concludes our presentation.
Any questions? Questions? No?
So basically, what will be your target market for this product?
Warehouses. We chose warehouses kind of at the beginning, just for loads up to 400 pounds, trying to go back and forth through a warehouse, putting loads on, taking them off, and just having a carrier kind of follow you without any input from you.
Okay, so it's up to 400 pounds.
Yeah.
Okay, I know this is a prototype, but what would you think to implement as to protect your components, because you're gonna be.
Yeah, of course, yeah.
So and I see that like the camera is exposed.
Yeah,
So
yeah. So at first, we were going to put all the electronics on the bottom and everything, but we needed the camera to be a lot higher because we had issues at the beginning. It was sitting so low that it was really hard to pick up the target. So somebody wearing a shirt, especially him being a lot taller, we would be able to pick him up really good. So we decided to put all the electronics on top so we can have like a little base to put the camera on top. And so we thought about in future work we can make kind of guardrails on the top of it so nothing can slide around and move. Yes.
For your specific load, what's the power requirement to actually move this?
So we took the specs off of the wheelchair motors. We got the specs from the wheelchair motors, where basically it provided a maximum, I think, 497.5 pounds or 397.5 pounds to go 5 miles an hour, I think it was. The specs on the actual motors from the wheelchair, we basically compared it to the weight of the actual robot to the wheelchair and use that information to predict how fast it was going to go or anything like that.
Yeah, but so what is the power requirement on those? How much power is required to move, say, 400 pounds with restriction?
We didn't do that testing because, like I said, we had the specs from the motors themselves. So from the manufacturer gave us the power requirements. I think, I can't remember, I think it was 240 watts in total was the, each motor provides 240 watts per each motor, but
Yeah, but
we use these, like I said, the specs from
right. So I guess the main question why I'm asking this is because you have 2 car batteries basically running this, right? Do you need 2 car batteries running?
You don't
this?
need to, but for the, because we wanted to get big batteries, we wanted to kind of weigh it down so we can have this one spin out of control, you know, when it accelerated too fast, which it did in some points, especially when it was trying to stop. So we wanted to weigh it down a little more and to have a longer capacity so you can actually operate it the entire day. But in reality, it only lasts about 4 hours with these batteries if it's running full speed. So you don't need to have these car-sized batteries almost, but we like to have it run as long as it can, and we try to extend the life of the actual system.
One other quick question.
Yeah.
Why is it faster with more load than
It
with
is not
less?
faster.
Oh, I thought I saw that. It took
No,
longer time. Sorry.
Yep.
Average
So-
speed. Oh, okay, I got you.
Average
Okay, I was looking at
speed
the wrong
is
time.
higher,
Gotcha.
no load.
Gotcha. Sure. Yeah. I saw time and speed and flipped it.
Yeah. Any other questions? Yes.
Yeah, well, he had nothing about moving your electrical. But have you thought about incorporating some kind of solar recharging system on this? Because you mentioned a warehouse.
Yeah.
Have you thought about something like that or some kind of charging station or?
So we initially thought of trying to take this thing outside and test it out there, and one of the biggest limitations on this is the actual camera itself. And so it's very, very receptive to different lighting. So if you have a target, say like a red shirt, and then it picks up the red shirt, when you get a shadow on it, it'll change the image to the camera, and it makes it very difficult to operate. So outside right now, it can't operate. Like it can work a little bit, but it basically works off of the size of the target it's detecting. And so if it gets to a threshold, it knows that it's, let's say, like 2 feet away. If you program it that way, it'll be 2 feet away from you, and it can follow you at 2 feet. But if the image itself gets too big, it knows that it's too close, and it'll back up. And if it gets too small, it'll continue to go forward, basically. And so when you have different lighting conditions, like outside, you have a lot of shadows and things, it'll block off certain parts of the target itself and shrink the actual surface area and think it's a lot further, so it'll actually come in tight if you use it outside. So we didn't really think about using it outside. We kind of tried to do it in a very nice lit warehouse and that kind of stuff. So we did it in a parking garage and it worked very well. Yes?
Are there limits to the autonomous? In other words, I noticed the camera's not rotating, so
Yeah.
you're not using the ability to look three-dimensionally around this device.
No, so basically we have, in the programming, we have 180 degrees, that if it can't pick up the target, the actual robot will stop and the camera will sweep, kind of back and forth, go up, sweep, back and forth until it finds the target. If it doesn't, then the actual robot itself turns 90 degrees, does its sweep again, and then if it doesn't find a target, turns 180 degrees, does its sweep again. So basically, like that, it can find the target, but it doesn't, the camera itself, the pan and tilt, only goes about 180 degrees.
Okay, and then the other question I had was that in your objectives, you said that the system was able to travel on different terrains.
Yeah.
Did you do any work to show that this could travel on different terrains?
No, so initially with the first prototype design that we had that we showed with the tank drive, that was one of our main goals, and we really wanted to be, use the tank drive to kind of keep it level whenever it went outside or anything like that. But as we got more into the work of it, we saw that we couldn't actually use the tank drive because of the expense and everything. Then we decided to use the camera, which you can't use outside, so we kind of narrowed it down to staying only on flat surface. As you can see, these batteries are only about an inch and a half off the floor, so it cannot go over anything, basically. It has to be a very flat surface. The environment for this robot has to be very, very, very tightly monitored. It has to have good lighting and very, very flat surface. So our future work is to kind of go around that and to use maybe a different sensor to kind of figure out how we can, especially lift up like you said, we don't need these huge batteries to operate, this robot, but if we want a longer life, we have to have the big batteries, and it's gonna be close off the floor, we can lift it a little higher, but then we have problems with tilting, and if we have a lot of weight, and if it's too high, then, you know, all that kind of stuff has to come into consideration. You had a question back there?
Yeah, pardon my ignorance, but can you explain to me what optical avoidance is?
Optical avoidance is just basically, right now, we don't have it, essentially that as this is following you, if something goes in its path, it's just gonna try to run it over. So optical avoidance is to actually detect something in front of it, so I can stop, maneuver around it, and continue following. Yes?
I'm just thinking about like, if you put this in a warehouse.
Mhm.
So if that's loaded with 400 pounds and it's coming at you at 3.4 feet per second, have you thought a way to, because you're relying just on the camera, and
Yeah.
if anything fails, if you have that amount of load coming to a person,
Yeah.
like, you know, the safety.
Yeah, I understand. So basically in our future work, like we said, that we want to make it fully autonomous, and what we really want to include is a remote cutoff switch, because that just kind of throws all the safety, you know, a lot better. Because right now we only have a cutoff switch on top of it, so if this thing goes haywire, we have to chase it and turn it off, basically. But, you know, a remote switch would be where we try to go. And also, right now, you can change the distance at where it follows you, so if it is coming at you.
And can you change the speed?
Yeah, so you can change,
Okay.
you can basically change the extremes of the speed, how fast it can back up and how fast it can speed up, and the max speed it can go and everything like that. You can change that. Any other questions?
Thank you very much.